Yeah.
Varun?
Yes, sir, yes. I was just admitting to the people who was trying to.
No problem. Varun, Navneet is also a co-host. Leave it.
Okay, sir. Okay. So, welcome to one and all. Welcome to the UL Space Club webinar session 61. We are 62. Now we are on the 62nd session of our webinar series, which we started during the COVID pandemic issues. As as an initiative to promote enthusiasm in students when they are stuck in home during the pandemic situation. So later we continued the sessions and we got continuous support from institutions like ISRO, DRDO, National Remote Sensing Center, and many other institutions like IITs, ISS, and IAST. With that support, we could continuously go with this kind of webinar sessions, and we could make best use of it as the students. And our students were also encouraged by the support given by the speakers who was getting presentations at this webinar series. So we are very happy to welcome all of you to this webinar session, which we are going to talk about Moon, which is our celestial neighbor, which is the one and only natural satellite of our Mother Earth. And so we are happy to have Dr. Smitha Thampi, who is a continuous supporter of UL Space Club, who has visited our space camp during our Trivandrum space camp last year. And we are very happy to welcome you, ma'am. Welcome to our platform. We will have a detailed introduction of our speaker by our mentor, sir. Before that, I have a few instructions for our students, and please use the chat window for your kind questions. You may have questions, as Chandrayaan 3 is the most prestigious project which ISRO have done. Most of you may have some questions related to moon exploration, especially about Chandrayaan 3 and Chandrayaan missions, Chandrayaan 1, 2, and 3. So you can ask about the questions in the chat window. Our student team will select questions from the chat window for the question answer session, and Mr. Navneet will be handling the question answer session. Other than that, please switch off your camera and mic throughout the session. When our speaker is talking, if you are also trying to switch on your mic, it will be an interruption to other students when they are trying to listen to our speaker. So please don't try to do that. Another thing, please don't try to share your screen. Our speaker may have a presentation, and if you are trying to share your screen, it will be an interruption to the presentation that speaker is doing. So please don't try to do that. Please switch off your mic and camera, and please don't try to share your screen. That are the kind of instruction for the participants. Please try to follow that. And you are all welcome to ask your questions, type your questions in the chat window, and best use of this platform where you can interact with the scientist or my. So once again, welcome all of you to the UL Space Club webinar session 62, and we will have a quiz competition after this webinar session. We will have a quiz competition about Chandrayaan and other moon-related moon exploration projects. We will have a quiz through the Google Forms. The quiz link will be available during the time of quarter times, and it will be active only after the session is winding up. So you can let's move on to the introduction of our speaker. We'll have a detailed introduction of our speaker, Dr. Smitha Thampi from Shadil sir. I kindly request Shadil sir to do so. Shadil sir.
Okay, thank you, Varun, for your wonderful introduction. And you are here, and we all are here for the past 61 sessions. This is a 62nd webinar that's going to happen here. And we really feel it's a little bit excited, and it's a wonder for us to continue these sessions for our children. And really, we feel it's a good environment for our science enthusiasts of this region, especially in Kerala and other state also. Students are also attending this program. And today's topic is the moon, our celestial neighbor. And it's a little bit scientific title given there, because in your childhood all the children call the moon as their uncle, like that. Now we turn everything in the scientific method. I think our speaker placed in that with that scientific temper with that, and we are thinking it's something different and something yet to be explored more regarding the suns. That kind of informations we are getting after the prestigious and proud endeavor of ISRO in Chandrayaan 3 that successfully landed on the surface of the moon. And after that, we have the Aditya mission. We are full of joy in our mind and proud about the ISRO. So we are here in the UL Space Club webinar session, 60-second webinar sessions. UL Space Club is the space club organized and founded and mentored by E.K. Kuti, former director ISRO, from 2016. That's happening here. We are conducting several space camps and science projects, student discussions, webinar, all these things. And Varun already stated that we started this webinar during the COVID era, and we are continuing. Every second Saturday at 3 p.m. all the children, all the teachers, and some of the scientists and even common people are joining with us. So we are proud to be here. Today we have the co-host here. Every webinar nowadays it is co-hosted by any school, and the school that is most interested in nurturing science among the children. Today we have Bhavan's Vidyalaya Ramanatagara with us, and that's the co-host happening here. Before we are going to that, let me introduce today's guest from VSSC, Dr. Smitha Thampi. Smitha Thampi is the scientist G in SPL, VSSC, and she was the part of Chase 2 and COPI payload Chandrayaan 2 orbiter mission. You know, we succeeded this Chandrayaan 3 with the help of Chandrayaan 2 orbiter that's still working there. We are proud, ma'am. With that, we could find the safe landing area or the smooth surface, flat surface, because of your attempts, sir. Every ma'am, it's there. Chandrayaan 2 orbiter still working there. We are proud about you, sir, ma'am, and field of research in the space, weather, and space. And before that, let me introduce her own institute, that is SPL, Space Physical Laboratory. It's a premier laboratory in VSSC, ISRO, aiming at the scientific understanding of the energies, dynamics, and chemistry of terrestrial and planetary environments and implication to the society. The genesis of SPL is closely entwined with the evolution of space sciences and space research in India, and dates back more than 5 decades. Dr. Vikram Sarabhai, with the support of Dr. Homi J. Baba, established Tumba Equatorial Rocket Launching Station TERS over the magnetic deep equator 1963, and established the Space Physics Division in 1968 to study the unique equatorial upper atmospheric phenomena. In 1984, the Space Physics Division has been elevated to Space Physics Laboratory with the mandate to carry out advanced research in atmospheric, space, and planetary sciences. Several outstanding results have been emerged from various ground, rocket, and space-borne studies carried out at SPL. Today, SPL has attained the status of vibrant research institution of the international repute with the front-ranking research. There, our ma'am is working, and we are proud of you, ma'am, regarding your contribution to the success of ISRO here. Dr. Smitha Thampi is a postgraduate in physics from Cochin University of Science and Technology, and he completed his PhD in University of Kerala and in the topic ionospheric tomography, and she achieved several awards and fellowship for her excellent contribution to the nation on behalf of ISRO. She received Bhatti Foundation Award in 2021 for her outstanding contribution in the field of plasma science and technology, instituted by Bhatti Foundation, awarded through Physical Research Laboratory, Ahmedabad. Ma'am, we have been conducting a plasma exhibition near at NIT, Calicut, in support of the Plasma Research Institute, Gandhinagar, and we know, then only we could know that plasma is that much of importance in the case of space science and exploration. And she achieved Nazi Scopus Young Scientist Award in 2017 and Women Excellence Award of the SERB, Science, Engineering and Research Board of DST, Department of Science and Technology, Government of India in 2013, and Young Associate of Indian Academy of Science 2011, Young Scientist Award at the Asia Pacific Radio Science Conference AP RASC 10, Toyama, Japan in 2010, Young Scientist Award URSI Gas at 30 URSI Gas Istanbul, Turkey 2011, and Japan Society of Promotion of Science JSPS Postdoctoral Fellowship in 2008 to 2010. It's all these recognitions shows that our today's speaker is well known not only in India, she's well worked in globally and it's globally accepted space scientist, and we are proudly acknowledging our gratitude towards ISRO in the achievement of Chandrayaan 3. This is the first time we are celebrating with an ISRO scientist the success of Chandrayaan 3 and Aditya. We proudly invite to this forum. Welcome, man. Okay. Then before the talk begins, we have the the co-host, that's the Bhavan's School, Ramanatagara, and I welcome all the teachers, principal teachers and students of Bhavan's School, Ramanatagara, to this forum. Then our founder and mentor E.K. Kutisar is there. I welcome Kutisar and veteran scientists and the students, some of the UL Space members continuously attending this program. I invite all of you, and I invite Mr. Saji, principal of Bhavan's School, Ramanatagara, make his presidential address. Welcome, sir.
Thank you, Shajil sir. Namaste all. Respected Kuti sir, Smitha madam, Shajil sir, and all other dignitaries on the meeting. Then we have from my school around 40 to 50 students and teachers. So we have from our school Mrs. Sharjina and Mr. Abhilash representing the physics department, and other teachers as well as students who are either in the space club or from different classes. So namaste and good afternoon to you all. It's a wonderful chance. Actually, we are really privileged. We are really privileged, and we are really proud that we are here on a podium where unimaginably big persons like Kuti sir, Smitha madam, and all others are here. We are very happy, and we feel proud and feel blessed. Actually, our school is very serious about inculcating space thinking, space science, and the notions of space. And we have been celebrating around 1 week. Before the successful soft landing of Chandrayaan 3, we have been celebrating a week named Vikram Week celebrations, in which we had two distinguished scientists from ISRO itself. One is Mr. Sanit, who is working in SAC. Then we had Mr. Jairam, of course, recommended by Kuti sir. And they came to one of them. Mr. Sanit came on online video conferencing. Jairam sir came to our school physically, and that was a wonderful occasion for almost all our students to have interaction with them. And I think we are really enriched by that. And I take this opportunity to thank deep-heartedly for such occasions. And it was actually it was the bounty of Kuti sir. I was constantly contacting Kuti sir. And it was his bounty that we had such a wonderful celebration, and we had a week-long quiz program and all those things. And now the students and the teachers in this school are well aware of the space science, and many of them have already become space enthusiasts. And many students, I would be feeling at least a few of them would be pursuing the space science in their future studies and career. So all these things are possible only because of Now India is in a premier position maybe ahead of all countries. Actually, after the stunning success of Chandrayaan 3, I think our space science graph has gone up. And I think this is a right opportunity for many of the youngsters to be enthusiastic and to be desirous of learning and getting into that field. I think we will be getting sufficient encouragement and backing from scientists like Smitha ma'am, who is present here. And we look forward to Uralangal Space Club and the mentor and founder of the Space Club, Kutti sir, and of course the convener and coordinator, Shahil sir. We look forward to our continued association with you. Thank you so much for giving me such a wonderful opportunity. I don't take much of my time because we have our esteemed guest, Smitha ma'am, who should be inspiring us. Especially the youngsters on the podium, inspiring them to be great scientists in the future, so that we will be having interplanetary, interstellar, and even intergalactic missions in the future. Of course, definitely from India, and maybe collaborated by all the countries of the world. And usually I am telling my students, and I have one of my favorite proverbs: the known is a drop and the unknown is an ocean. The known is a drop and the unknown is an ocean. I think this is correct with regard to all knowledge. The human beings are very limited, but the knowledge realm is endless, unfathomable, no limits. So every moment you have to achieve new knowledge. Every moment means even from birth to death, from womb to tomb, you have to be desirous of gaining knowledge. And I think this is all the more correct in the case of space science, because we are nobody. If you take the huge size, breadth, and length of the universe, even now unknown to us. The observable universe is only known to us, which even that is beyond the reach of all human technology right now. But the known is a drop, or the unknown part of the universe, unknown part of the cosmos is that which bewitches us, that which magnetically attracts us to find out more and more, to make more researches, to go more deep into with the scientific spirit, to make more and more space or interplanetary, maybe interstellar explorations, to know more about it. I think this is not only now. Previously, it was only an enthusiasm. People were wondering really what is moon, how to reach moon. But now the things have I think, turned due to the advancements of technology. Like now the space science is more or less used for the benefits of man. Like the energy needs, we have the huge energy need. We have the human being. I think all of us are aware of helium-3, which is more abundantly available in moon, but very less available on Earth, and which will be catering to the huge energy needs of human being of the earthly institutions. So this type of I think the business side or the beneficial side of exploring the space and getting into space science is now becoming more and more relevant. I think this is a good turning of the history, because now the youngsters will be more and more interested for the benefit of humanity, for the improvement, for the enhancement of different facilities of humanity. You go out interplanetary so that you can bring greater good for the humanity, for the whole world. I think that is a good turning the area, the turning point. Previously, it was only out of enthusiasm, but now it is more of beneficial for the whole of humankind. I am very happy that Kutti sir, Smitha ma'am, representing ISRO, such a premier institution in the world, our Indian institution in the world, they can lead us, they can enlighten us in this regard, and more youngsters will be attracted, and I think our Earth will be a much more wonderful place to live in. And let there be a lot of scientists, even from this podium. I sincerely wish let there be the research skills, the research mentality, and there should be scientists from among us. That is what I have to just ask to our my students as well as the youngsters on this podium. Thank you all. Thank you so much. Thank you, Shajil sir. Thank you, Kuti sir, Smitha ma'am also. Thank you very much. Yeah, exactly. Yeah, yeah. Thank you, sir.
Thank you, sir. Thank you, Kuti sir, Shajil sir, and the principal Vidyasram for this wonderful opportunity to talk to you. I have been, as Varun told, I have been there in the last year with the UN Space Club for the space camp, and it was a real nice opportunity. It was really a good, very fantastic day for us. So it's always very nice to see the young minds and to talk to them. So thank you for this opportunity, and also on behalf of ISRO, I thank each and every one of you for your encouragement and this very heartening applause for the success of Chandrayaan 3. So we will talk about Chandrayaan 3 also. So let's start the today's session. I think I'm audible and clear. So I'll just.
Yeah.
Okay. Thank you. And now I'll share my screen. It's a laptop. I'm just trying to, yeah. My screen is visible. I think I'll do once again. The screen share. Yeah, thank you. So today's topic is the moon, our celestial neighbor. So I'll be first talking about some facts about moon and initial missions to moon. Then I'll talk about Chandrayaan 3, especially the science of lander and lower payloads. And then I'll be talking about the future. So moon, as we know, has been a deity and a timekeeper for the ancient world. And even one of the most ancient texts, that is the Rig Veda, has its reference to the moon, that, "O moon, we should be able to know you through our intellect." So moon has been a deity, and also moon has inspired our literature immensely. It has been a part of our literature as a reflection of beauty or a reflection of love and so on. But after the invention of telescope, moon was naturally the first focus for earlier astronomers because it is actually our celestial neighbor, or one of the closest objects which could be seen. So afterwards, there are several moon missions, and the famous statement of Neil Armstrong when he stepped onto the moon that's one small step for man, but a one giant leap for the mankind. So today, most of the spacefaring nations across the world has planned or has lunar missions. And many scientists propose lunar-based astronomical observatories because moon doesn't have a very significant atmosphere. So the most ambitious visions for lunar exploration at this stage are NASA's Artemis program, where they're planning or renewed interest and they're planning to have a manned mission, and European Space Agency's, that is ESA's Moon Village. Moon Village is basically a collaboration between several national space agencies and private companies is being envisaged for scientific and technological activities, exploiting resources as Principal Sir was telling, tourism and underground habitats and so on. Your imagination is basically the limit. So, basic facts about Moon. Moon is the only natural satellite of Earth with a perigee of around 3.5 lakhs kilometers from Earth, and its orbital period is around 27 days. Sidereal rotation period is 27 days with a synodic period. That is, when we talk in reference to Earth, it's 29.5 days. Its inclination to the ecliptic plane is around 5 degrees, and mean radius is around 1700 kilometers. It has around 27% of Earth's mean radius and mass about 1% of that of Earth. So this body is a moon or a natural satellite of Earth, which is not a very small moon, but it's not the largest moon also. You can see some of the solar system moons here, and we can see that Earth's moon, that's the moon, is almost fifth in terms of size, where we have several smaller moons also of Galilean satellites. So this moon is not very small. And there is one interesting part of the moon, as we always see the one side only from Earth. So that is known as the near side, and we see only the near side from Earth because it's the time taken by the moon to complete its orbit around Earth, that is the 27.3 days, is same as the time taken to rotate around its own axis. This kind of property is known as synchronous rotation. Because of that, we are able to see only one side of the moon, whereas the other side of the moon, which is known as far side, is significantly actually different from the near side, that we will see as our satellites have given pictures of the far side as well. Now, as I told, it's around 3.5 lakhs kilometers and slightly elliptical orbit. Here I am just drawing it as a circle for simplicity. And where is the moon in its orbit? So, as we know, Earth is a planet with a significant magnetic field, and this magnetic field produces a magnetosphere around Earth. Basically, it should be a dipolar magnetic field, but because of the presence of sun, the particles and the magnetic field always comes towards Earth, and it compresses on one side, that is the day side, and then there is an elongated magnetotail on the other side, where the supersonic solar wind comes and becomes subsonic due to the presence of this obstacle, and there is a bow shock which is formed. That is, the supersonic motion of the solar wind is slowed down to a subsonic motion, and Earth's magnetosphere doesn't allow it to enter into the planet, and it goes through the magnetic tail region to behind. So this is the condition, and our moon spends most of the time in the upstream or direct solar wind, that is around 2/3 of its orbital time around, and then the rest of the time it spends within the magnetosphere. So we see the synodic period, which is a successive recurrences of the same phase. We can see that the new moon phase and the full moon phase occurs when the Earth is in the upstream and Earth is in the magnetosphere, as all know. Now, as I told, the near side is the one which we see with some marks or some dark regions, but the far side is not looking like that. So this is basically from Clementine Mission, and this is a taken at this image is taken at 750 nanometer. We can see both the near side as well as the far side here. Now, as I told, the earliest observations by Galileo himself was using his telescope, and he saw these bright regions as well as dark regions in the near side of the moon. So, yeah. Okay. So when Galileo observed the moon using his telescope, he saw that there are bright regions as well as dark regions. He thought that these bright regions probably are mountainous, and so he called them as highlands. And the dark features which he saw was, he thought, probably like seas, and then he called those as mares. Mare is the Latin word for seas. And now we know that there are no seas and on the moon, but still we keep the name mare regions for these dark regions. Now we know that these bright and dark regions represent material of different composition and ages, and mares are basically impact basins or basaltic plains formed by very ancient volcanic eruptions. So these are around 3 to 3.9 giga years or billion years old. You know that Earth's around 4 billion year old. So these regions have different ages, or these are materials of different ages. Now, we have seen this mare basaltic region, which are relatively younger than the highlands, and these volcanic basaltic regions are, many of these regions are named like Mare Imbrium, like this. So we have, because of our Apollo missions and all, we have some information about these regions, and these regions are named also. Now, let's talk about the early missions to the moon. So, 1959, Luna 1 was the first mission by that time Soviet Union. That was a moon flyby. And 1959, again, Luna 3 went and given the first images of the far side of the moon. And I think my presentation disappeared. Let's see. No problem. No problem. It's visible, no? So the first images of the far side of the moon, and as we know, this was a period of space race between USSR, that is elsewhere Soviet Union and United States, and so US entered in the picture by Surveyor 1 mission, and they really made a soft landing on the moon in 1960s, and then the famous Apollo program started. Apollo 8 was the first manned spacecraft to reach moon's orbit and return. And Apollo 11, as we know, on 20 July 1969, first human being stepped on the moon. And then 3 years, this Apollo program continued. And Apollo 17 was the last manned mission in the Apollo era. And that mission, interestingly, took a real professional geologist to moon, who could spot signs of alteration or impacts in the moon during its initial years. And Commander Eugene Cernan became the last man to walk on the moon. And the Luna program also. And in 1976, the last, before this recent Luna 25, the last of that era was Luna 24. And this was the era of the space race between the Russia and the United States. And then a renewed interest in moon came in the 1990s. So by this time, the space race actually ended. And this is a space era of present era is actually an era of space cooperation, where several countries cooperate and make instruments and go. Even in in every field. Now the competition has given way to collaboration, which is a very interesting or nice thing to see. So Japan has demonstrated its technology in 1990s. 1994, the NASA mission the Clementine mission gave the first complete image of the lunar surface, including the poles. And that mission, interestingly, indicated that there could be ice at the bottom of a permanent shadowed crater at the moon's south pole. So there itself we can see that South Pole is an interesting region. And this just gave an indication of ice. And there are permanently shadowed craters at the moon's south pole. Then we have the Lunar Prospector of NASA, which gave surface composition, lunar mineralogy, measured magnetic fields around the moon. Then ESA has, and Japan has another mission called Selene or Kaguya, which was actually a very high definition image data from the moon. China also entered into the lunar exploration with the Chang'e mission. And then we had the Chandrayaan 1. So Chandrayaan 1 has actually revolutionized our understanding on the moon. In fact, we can really say that the lunar exploration history is divided into two, before Chandrayaan 1 and after Chandrayaan 1. This I'm not just talking because of our national pride, but it's really because Chandrayaan 1 had such a revolutionary discovery of moon, on moon, which many of you may be knowing. But before going to that, Chandrayaan 1 also had a small craft called the Moon Impact Probe. This was designed to impact on the moon, not a soft landing, controlled soft landing, but an impact on the moon. And this was actually designed because we wanted to test systems for future landings at that time. And then also this has given some understanding on very important clues about a very thin lunar atmosphere before crashing on the moon's surface. So it also crashed near the South Pole only on 14th November 2008. So as I told, we can divide the history of lunar exploration into two, pre-Chandrayaan 1 and post-Chandrayaan 1, because Chandrayaan 1 could discover the presence of water in moon. As we know, Chandrayaan 1 was an excellent example of space cooperation, where our PSLV has launched the Chandrayaan 1. Spacecraft was built by us with instruments from elsewhere also, and the US had a moon mineralogy mapper, which was a near infrared spectrometer, which showed absorption features near 2.8 to 3 micrometers on the surface of the moon, which this absorption in this wavelength indicate the hydroxyl or water-bearing materials. So this was very big discovery in terms of science, and it appeared in the science journal. Now, as I told, the moon mineralogy mapper of MIP also had an instrument called a mass spectrometer, which can measure the composition of the atmosphere, very thin atmosphere of moon. So what it did is that while it was impacting, while it was released from the mother spacecraft, that is Chandrayaan 1, and it was falling towards the moon surface, during its measurements of the very thin tenuous atmospheric composition, and it could detect the presence of water, that is AMU 18, that means H2O, H2 and O16. So in AMU 18, we could see clear signals of water when it was very close to the South Pole and very close to the surface. So this has given indication that the water could be present in the vapor form in the very tenuous atmosphere of moon, whereas moon mineralogy mapper gave the presence of water in the form of OH radical or water-bearing materials on the surface. So these two observations very conclusively told that there is water in the moon, and this really sparked a much greater or a renewed interest on moon, and it also showed that the permanently shadowed region or south pole of the moon is a very, very important region and to be explored. So not only that, Chandrayaan 1 had other discoveries also. So one is a mini magnetosphere of moon. So as I told, when a magnetosphere is present, it can deflect the charged particles from the sun, and that is how the Earth, which is having a full-fledged magnetosphere, is protected from the solar energetic particles. So, but when the moon is present, we think of moon as a very dry or a very rocky body, and it indeed doesn't have a rotating core or a liquid core and all. It doesn't have. So we don't expect a dipolar magnetic field to be present for the moon. But the observations showed that over certain regions, the particle flux is much less compared to the particle flux observed on the other areas. So this means that there is a significant interaction of the solar wind with the moon at that regions, and this is with the moon, and there is a reduction because some magnetosphere could be present at those regions. So this magnetosphere is called a mini magnetosphere, and that is an excellent example of crustal magnetic field, not like a dipolar magnetic field originating from the core. This is also a discovery from Chandrayaan 1, and this instrument is called SARA, Sub-KeV Atom Reflecting Analyzer, which is a joint project between a Swedish group and Space Physics Laboratory VSSC. So, and as I told, moon has an atmosphere which is very tenuous, which we understood even from the Apollo measurements itself. So that's why we had an instrument which was to measure the atmosphere. Now, how this atmosphere is formed? Moon is susceptible to impacts, and a steady rain of asteroids, meteorites, and comets strike the surface. So over the billions of years, the surface has been ground into fragments ranging from huge boulders to powder. And this surface of the moon is covered by a very powdery surface called lunar regolith. And then the lunar regolith is the surface from where the atmosphere originates, and we can see that the primary mechanisms generating exospheric atoms include photosimulated. Photo means light, and light from the sun simulates desorption of material. Solar wind can hit directly and sputter these ions. Meteoric bombardment can generate particles into the surface. Radioactive decay of materials can generate material into the surface, and also thermally, because moon doesn't have a very significant atmosphere. It has huge thermal variations, and thermal desorption also can release materials into the surface. Now, since it doesn't have a very huge atmosphere and it is continuously in the rain of solar wind, I can say, then it can be lost to space because it can be photoionized, because solar UV radiation is always present. And as we saw in the case of Earth's magnetic field itself, the solar wind or Earth's magnetic field can sweep these particles, because especially for ions, because these particles can be given a very easy pathway through the magnetic field. And as we saw, it can be trapped in the cold or permanently shadowed regions also. That's the water is basically trapped in the permanently shadowed regions, or it can be bonded chemically to active surface atoms. So this is a very dynamic equilibrium which is happening, and this very tenuous atmosphere is present. So when we talk about Earth's atmosphere, we know that it has a very considerable thick atmosphere of around 10⁻⁹ per centimeter cube is the number density of particles near surface. So if you compare with this, the moon has a very thin atmosphere because its number density varies around 10⁴ to 10⁵ centimeter cube. You can see that it's several orders lower than the surface, the atmosphere of Earth. So such atmospheres have a peculiar property. What happens is because when we have this atmosphere, very thick atmosphere, the atoms or molecules in the atmosphere collide with each other very frequently. So, but when the density decreases, the collisions also decreases with respect to the height or the altitude from the surface. This happens even in the Earth atmosphere, that the number of collisions among particles decreases with respect to altitude. Now, there is a region where the distance between two collisions or the mean free path between the two collisions is very high. That kind of regions we call as exosphere. And in the case of Earth, for example, this exosphere starts around 450 kilometers, where the mean free path or the number of collisions becomes very, very low. Now, in the Moon, since the number density is so low, the exospheric nature or the exospheric behavior starts from the surface itself, which we cannot expect in the case of Earth. In the case of Earth, we have so many molecules, and that's why we call it as air, and then we talk about air parcels and eddies, moving wind forms and all that. But in the case of Moon, whatever we encounter around 500 kilometers or 400 kilometers altitude at Earth is happening at the surface itself, and that's a kind of class of atmosphere called a surface-bounded exosphere. Not only Moon, Mercury also has a surface-bounded exosphere. As we know, the Apollo measurements indicated this for the first time, and we know that Moon's atmosphere is known to contain noble gases such as helium, neon, argon, and other elements such as sodium, potassium, and magnesium. So MIP Chandrayaan-1 has observed argon, neon, helium, and it also indicated the presence of carbon dioxide. So after Chandrayaan-1 also, there were several missions, the LRO, Lunar Reconnaissance Orbiter. You might have heard about the LRO taking pictures of Chandrayaan-2 lander and Chandrayaan-3 lander now. And also the GRAIL and Chang'e mission. Chang'e mission had a lander and a rover. And then LADEE mission was from NASA. That was an equatorial orbiting mission. Chang'e 4 from China was the first lander and rover mission to the moon's far side. So there were several missions. And then in 2019, we had the Chandrayaan-2 mission. Orbiter payloads were as follows: terrain mapping camera, Chandrayaan-2 large area soft X-ray spectrometer or class, and solar X-ray monitor. Then there was an orbiter high-resolution camera, which also imaged the landing site for Chandrayaan-3 also, which gave very valuable information about those regions. And there is an imaging IR spectrometer, which is capable of detecting water on the moon. There is a dual frequency synthetic aperture radar, Chandra's Atmospheric Composition Explorer 2 or CHASE-2, for which I was also a part. And there was a dual frequency radio science experiment, DFRS. So all these experiments are working well and giving good data. The lander module unfortunately couldn't soft land. The point where it crashed is known as the Tiringa point as well. So some results or glimpse of some results of Chandrayaan-2. The X-ray spectrometer class on the orbiter has mapped the abundance of sodium on the moon fully on the lunar surface for the first time. The Chandra's Atmospheric Composition Explorer 2 or CHASE-2, our payload, is a mass spectrometer similar to the MIT Chandrayaan-1 mass spectrometer. This has made the global distribution of argon-40 in the tenuous lunar exosphere. Previously, LADEE had measured the argon-40, but since it was in the equatorial orbit, it didn't measure over the mid-latitude regions. Previously, Apollo landings also were on the equatorial plane. So the mid-latitude and high-latitude regions of Moon were mapped by the CHASE-2 for the first time. And the XSM, the class, as I told, how it works is basically it measures the soft X-ray. It is a soft X-ray spectrometer, and the soft X-rays are from the sun, which is emerging. So there is another X-ray spectrometer which is looking at the sun, which provides context information for class whether these X-ray emissions are occurred from the sun. So this X-ray spectrometer is actually the only spectrometer with the highest time cadence for measuring the solar X-ray spectrum of the sun. So this payload just not gives only supports class to give the lunar science. It also is very important in terms of the solar physics. And this has yielded very interesting observations of the microflares and about the elemental abundance in the quiet sun corona. As we know, solar corona is still a mystery, how the coronal temperatures are so high. So these microflares and such observations are very, very important in terms of understanding the solar corona. So as I told, all these instruments are still working fine, and you will be able to see more and more results in the coming years. So coming into our most interesting or the talk of this time, Chandrayaan 3, as you know, August 23, Vikram has landed successfully on the moon. The soft landing has been successful, and the point is now known as the Shiv Shakti point. And on the next day, a rover that is called a Pragyan has successfully took a walk on the moon. Now, let's see what science it does. This rover and lander had payloads. So what science or what is the betterment in lunar science these payloads can bring about, or these payloads are expected to bring about? Let's see what are they for. So first experiment is called radio anatomy of the moon's hyperbound atmosphere, Rambha. That is basically a Langmuir probe. A Langmuir probe is basically, maybe you might have seen Langmuir probe in the plasma experiment, plasma meeting last day. Langmuir probe is a very special instrument which can measure the plasma, including ionospheres or even laboratory plasmas, etc. This basically is a charge collector which collects the charge and generates the current. And when you change the voltage, the probe responds accordingly, and the voltage to current curves can be used to understand or estimate the density of the plasma, that is the electron density, and also the temperature or the energy of the plasma, that is electron temperature. So Rambha LP was designed to measure the near surface plasma density and its changes with time. Now, this payload is developed by Space Physics Laboratory, VSSC. And so now the interesting question is why we should expect an ionosphere on moon. As we know, the Earth has an ionosphere. Many planets also has ionospheres. But when we talk about a very small body with a very small gravity and a very, very tenuous, almost airless like atmosphere, how we should or why we should expect an ionosphere. The first convincing evidence for an ionosphere came in the 1970s from Luna 19 and 22. So what they were orbiting at the moon at the very close range, and the orbiter sensed a layer of charged material. Now, how is this possible? And as I told, the solar wind always interact with the moon and its near surface and environment, so it can ionize. And this ions originating from this regolith-covered lunar surface and exosphere contribute to forming the lunar ionosphere. These lunar ions, because once there is an ion flow, that is solar wind flow with a magnetic field, it will be rapidly entrained, or it will just move with the solar wind flow, or it can also go back to the lunar surface. So it actually, once the ions form from the neutrals, these ions represent a dominant pathway for the loss of this exospheric species, because once an exospheric neutral becomes an ion, it has larger probability to get lost by the solar wind flow. Now, this is the picture as a representation of what I was just telling. The lunar surface, which is charged, and which gets charged, and these ions and electrons are formed at the lunar surface. Now, one more thing is that, as we told, the lunar surface is covered by a regolith, and it is an extremely dusty place. So the floating dust could provide the answer of how the ionosphere is sustained, because these particles, UV rays can ionize these dust grains. One is that this dust grains can be ionized, or secondly, these ionized particles can be attached to these dust grains, so that their lifetime could be little more. And there is a variability, as I showed earlier. The moon may be at some point of its time, it will be in the geomagnetic tail, and some other point it will be completely seeing the solar wind or in the upstream condition. When people have seen that when the moon passes through the geomagnetic tail region, its ionospheric presence becomes more and more important. So as we saw, this lunar ionosphere is the source of lunar ionosphere is the regolith covered lunar surface, and with a key role of dust. It is important to observe the ionosphere in situ from near lunar surface, because this ionosphere is not a very large ionosphere as in the case of Earth. We have 10 raised to 6 say 10 raised to 6 particles per cc and all around 200, 250, 300 kilometers. That many particles or that many ionization is not expected in the case of moon, and it doesn't extend to very high altitudes also, because its atmosphere is very tenuous. So the best place to see the lunar ionosphere will be from near surface, and Ramba LP for the first time does exactly this. So this is a picture of the probe deployed from the lander, which is taking measurements of the near surface lunar plasma. It has taken a full lunar day of measurements. You can also see the rover in this image. Now, the second experiment is called the CHAST Chandra Surface Thermophysical Experiment. This is to carry out the thermal properties of lunar surface near the polar region. This is also developed by SPL in collaboration with PRL Ahmedabad. And so, why an airless small body or a very tenuous body with a very tenuous atmosphere has a thermal environment which is so important? Yes, because its atmosphere is not significant. That's why your moon's thermal environment sees a very extreme temperature swings. Surface temperatures can range from 20 Kelvin to 450 Kelvin, one of the widest ranges of the solar system. And we have, as I told, there is LRO. LRO has given a lot of our understanding about the surface temperatures of the moon. But as we know, we have the moon is covered by the lunar regolith, and we do not have much information about the temperature with the depth within the first few centimeters about the regolith, or the behavior or the nature of the regolith, how it varies. That information we never had, especially in situ. So CHAST gives exactly this kind of information. As I told, due to the lack of atmosphere, moon has extreme variabilities of temperature. Here is a picture where the surface temperature ranges of various bodies can be seen. So as I told earlier, Mercury and Moon are two examples of surface-bounded exospheres, and you can see the extreme temperature ranges for these two bodies. Mercury is very close to Sun, so it shows extreme temperature variations. Same is the case with Moon. It also shows minimum is very low and maximum temperatures are very high. You can see the body with significant atmosphere, Venus, Earth, shows the ranges of temperatures are much lower. And even Mars has significant temperature variations because its atmosphere is tenuous. But because of its distance from the Sun, the higher temperatures are not as high as, and other properties of the atmosphere, it's like carbon dioxide cooling and all, its higher temperatures are not as high as that of the Earth. And you can see the body Ceres, which is an asteroid, which also doesn't have an atmosphere, and so the temperature ranges are high. And Pluto, Io, Europa are very far from Sun, and the temperature ranges are small. not only the distance from the sun for Mars, in the case of Mars, the carbon dioxide dominated atmosphere and the inherent properties decides its temperature structure. So in the case of Moon, because of its low thermal conductivity and low thermal diffusivity, the surface temperatures are sensitive to features. For example, if you have a surface which is tilted towards the sun, that region will get a lot of temperature, or that region will get hotter and hotter. But because of its low thermal diffusivity, it will not conduct this heat to the nearby region. So this tilted region will remain hot, whereas a surrounding region can remain very cold. And shadowed regions will be significantly colder compared to illuminated regions. Also, there is low thermal inertia. Surfaces tend to reach very cold temperature at night because of its low thermal inertia. It couldn't sustain the heat. Likewise, very low albedo or low reflectance surfaces can reach very high temperatures during the day. So this temperature in the lunar surface or regolith is highly variable. So any point measurement is very important to understand the region properties of that region. And that's why Chastain did this experiment. So also there is a practical importance which is coming up, because people have started thinking about lunar bases and all. So understanding this low thermal conductivity material or the regolith is very important. People have even thought about using this low thermal conductivity material to store heat and provide energy. Like that thinking is there. So understanding this regolith is very important. That's why the Chastain measurements or the results from Chastain will be very good. Another lander payload is called ILSA, that is Instrument for Lunar Seismic Activity. This can detect and measure seismic activity around the landing site and also delineate the structure of the lunar crust and mantle. Always, the seismic activity of any body gives an understanding about how active its internal surfaces are, and it can also give understanding of its crust and mantle. In the case, this is developed by the ISRO Laboratory for Electro-Optic Systems, LEOS. And why this is important in the case of Moon is because not only the internal energy, like earthquakes, mooncakes are produced by the results of meteorite hitting and also by the gravitational pull of the Earth. For example, when a meteorite hits the surface, it can generate a shallow mooncake, which can be measured by instruments like ILSA. Also, as we know, Earth's oceans are pulled by moon. That is that we call as a tidal pull. Similarly, Earth also inserts a gravitational pull for the moon. So it actually, moon being a smaller body, it squeezes and stretches this moon's interior, and this can also create very small movements in the lunar crust. Also, we know that all these planetary bodies' interiors are getting cooled in a very long or large time scales, and this when the moon surface, since the moon surface crust is brittle, when it cools and shrinks, it forms faults. And then the heat from the sun also can produce thermal quakes. And as we told, there is a large thermal difference. This can also produce quakes in the moon. This is one of such fault which is formed and measured by the Lunar Reconnaissance Orbiter camera, which shows that because of the shrinking of the moon by the loss of thermal energy, these fault lines are formed. So it is indeed present. So how do we measure fault or seismic activity by an instrument which is placed on the surface? That's a technique known as accelerometer, which we are all familiar. Even our mobiles or cars, they have these accelerometers. And But what is the kind of measurement which we want to, what is the kind of movement which we want to measure is very, very low compared to that of a real acceleration we are measuring in a mobile phone or so. So these are very low noise accelerometers and very sensitive accelerometers. They are called seismometers. So basic technology or the basic principle is that of an accelerometer, but they are so designed to be very sensitive and very low noise, and this can detect seismic waves. And ILSA comprises of a cluster of high sensitive accelerometers, 6 in number, which is doing exactly the same, and it has recorded the movements around the landing point, the Shiv Shakti point. But one thing we have to remember is that it not just measures the natural movements of the moon surface, it can also measure the movements created by us. For example, as I told, the CHAST instrument, when it penetrated around 8 centimeters into the lunar regolith, the ILSA could detect its motion. When the rover was moving, it could measure all the movements by the rover. Likewise, all these small motional waves were detected by the ILSA payload, and some of them they are actually thinking to be natural also. We can see the famous image where Vikram lander is seen by the NavCam image of the Pragyan rover, and we can see both the CHAST and the ILSA instrument. So the ILSA instrument has touched the lunar surface and it is lying on the lunar surface, so it can measure these activities or the seismic motions, and CHAST has penetrated indeed. We can see that the tip has got into the lunar soil, and the temperature variations we observe is indeed about the first 8 centimeters or so in the lunar regolith. This is the, as Sir told in the introduction, the Chandrayaan 2 orbiter camera has given us a very beautiful image of the planar region of the landing site, and this is the picture also. So, rover payloads. The rover, Pragyan rover, had 2 important payloads: the alpha particle X-ray spectrometer APXS and the LIPS payload, that is the laser-induced plasma ablation method. So both these payloads were or are to understand the elemental composition of the lunar soil and rocks around the lunar landing site. First, coming to alpha particle X-ray spectrometer. This is developed by Physical Research Laboratory with support from Space Application Center and URSC. So, how it measures the elemental chemistry? This is using the alpha particles and X-rays. So, this instrument carries, as we know, alpha particle is basically radioactive decay material. So, this instrument carries a very small plasma alpha particle source, and these alpha particles are emitted to a target which is on the lunar surface, and the reflected because of the presence of the hitting of the alpha particle into the target, it emits or excites some X-rays, and also there is the alpha particles which are the resultant alpha particles also, whatever we have sent. So these energy distribution of this outcoming alpha particles will be different from what we have sent, and the X-rays also. The X-rays are characteristic X-rays emitted by the target. These two are measured by the detectors. The alpha particle, the change in the energy distribution of the alpha particle tells how the alpha particles were absorbed by the material, and the excited X-rays also. Both are measured by the detectors, and this is analyzed to determine the elemental composition. As we know, all these materials will have very like signature, fingerprint kind of signatures in terms of their X-ray emissions or electronic emissions and all. So all these, in the case of alpha particle X-ray source, we are using the X-ray emissions as the signature for a particular material. Now, the lunar laser-induced breakdown spectroscope or LIPS also gives the chemical composition and mineralogical composition. This is also developed by this LEOS Center of ISRO. And here, what we do is a high-power laser pulse is used as an energy source, and this energy source will be given as shots. So you give, say, 10 shots or 15 shots, and then when it hits the lunar surface, the target source a small region, it will ablate atoms or form a very short-lived high-temperature plasma. Now, once we stop this laser pulse, this plasma has to cool down, and it is in an excited state of electrons in the outer orbitals. So once this plasma cools down, or once this ablation stops, this plasma will cool down. All this will be happening in seconds time, and this excited or even milliseconds time, and they have characteristic emissions. So each material will have its characteristic emissions, and that is how we identify materials from these lines. Now, this is the track of the rover, which is imaged when the rover was in an appropriate position and to image a previous track. And this is the total distance covered by the rover on the lunar surface, around 100 meters. Then it had different kind of motions. It took a retraction, it took a turn, and all that it could do in the one lunar day. Now, there was a very interesting experiment which was carried out in the last phase of this 14-day observations of one lunar day observation. Why we could do this is because the lander is equipped with altimeters, velocimeters, propulsion system. For, as you know, you all might have seen the landing video, and we can see that there was a propulsion system, and it was hovering in few meters above, and then only it landed. So it had its own propulsion system with control electronics. It has its own navigation, guidance, and control system, and it had a lot of hazard detection and avoidance algorithms. So presence of these equipments helped us to land, soft land very safely. It also prompted us to do one experiment known as the HOPE experiment, where the propulsion system was activated for some time and ignited for some time, and it could really lift off from the moon surface for around 40 centimeters, and it moved a little bit around 40 centimeters, and then landed on a different, slightly 40 centimeter away at a new point. So this is known as a HOPE experiment, and this is the two adjacent locations before the HOPE and after the HOPE experiment. This experiment is very important because by this experiment we have proven our capability to lift off from a different planet or a different celestial body, which is very important when we plan our sample return missions or later human missions or something like that. So what is store for us in the future lunar explorations? I am not just talking about Indian missions. Science is really universal, and space is all about space cooperation now. So first I will talk about the Artemis mission. And with Artemis 3 mission, NASA will land the first woman and first person of color in moon, and this will be in collaboration with commercial and international partners. And the first long-term human robotic presence on and around the moon is planned with this very ambitious mission. Now, the NASA is all set for this Artemis 2 mission, where a first crewed test flight to the moons in Apollo. This will just have a flyby of the moon. It will not soft land on moon. The crew will be there, and they will be back in around 10 to 12 days, in a journey of around 10 to 12 days in the case of to Earth to Moon and back. So we all are looking forward for the human presence in Moon. So when we talk about India, India's next big mission is Aditya L1. As you have seen, the PSLV has successfully launched Aditya L1, and Aditya L1 is on its way to the Lagrangian point. So I just thought I'd share 2 slides on Aditya L1. What is L1? Or why L1 point is important? There are this L1 or Lagrange point is named after the scientist Lagrange, and these are actually gravity points to objects. And this is basically a body problem where a third body can be placed in a very gravitational, in a stable. There are stable and unstable Lagrangian points. There are 5 points around Sanath Lagrangian. There are 5 Sanath Lagrangian points, and as you can see in this figure, at L1 we can observe sun very continuously. So this is our continuous solar observatory at this point. So Aditya L1 will do such measurements. For example, the L5 is another very interesting point where we can observe the sun continuously, and even before any solar disturbance reaches Earth, L5 will be able to see. So these Lagrangian points are very, very important points as far as solar and astronomical observations are concerned. For example, L2 is a very interesting point for astronomical observations. So likewise, coming back to the imaging, which will be imaging the solar disturbances. There are observations in the UV wavelength, X-rays, hard X-rays, soft X-rays, and particle measurements. As I told, we are in a continuous flow of solar wind. So this payload called Aspects and Papa, these 2 will be measuring the solar wind, and solar wind also carries its own magnetic field. So the MAG payload will be measuring the magnetic field from the interplanetary magnetic field. So this is very important because we have something called the space weather. Space weather, like we have weather in the Earth, we talk about short-term changes like wind, rain, precipitation, etc. in the lower atmosphere. In terms of lower atmosphere or the meteorological weather, we have a very dynamic weather in the upper atmosphere also, which is known as the space weather, which main driver of which is the sun. So what happens is that when the solar induced transients are present, these are very important to understand. However, the meteorological weather is important for our lives in the surface of the Earth. The understanding the space weather is that much important for our space assets at those altitudes, because these high energy particles and high energy particles, etc., can have very big disturbances to our electronic assets in the very high such altitudes of low Earth orbit or higher altitudes. And also this space weather is important in terms of communication, navigation, etc., because it can cause radio blackouts and things like that. So we always talk about the geomagnetic disturbances, solar energetic particle disturbances, and radio blackout disturbances in different levels. And people continuously look at the sun and its particle environment, like NASA and all. Similarly, now we have our own observatory to look into the space weather. That's a very important milestone for Indian space science. So, lastly, I just want to talk about this aspect. All Indian missions data or ISRO missions data are publicly available in Indian Space Science Data Center. Many of your interesting students can register and see Chandrayaan 1 data, Mars Orbiter mission data, Chandrayaan 2 data, AstroSat data, and all that. So this requires probably a registration, and many of the images are there as images itself and data also. So this will be a very interesting thing to explore. Thank you.
clear to our children and all of us. All these things we get a glimpse only from the social media and newspapers. Now you connected the basics of the science and everything here, and we have students here. They get a good chance to interact with an ISRO scientist who is directly involved with Chandrayaan missions here. Then I invite.
Yes.
Then before the question answer session, I invite E.K. Kuti sir, our mentor and founder of your space club, to make some comments. Welcome, sir.
Thanks, Shajil Mash. It's a wonderful afternoon. You know, an exciting Chandrayaan 3 has actually made our nation celebrate it as a very huge national achievement. So we have Dr. Smitha here representing the entire ISRO for us to see what all happened in Chandrayaan 3, the mission angle, from the mission angle, what payloads, they kind of experiments, the carried, things like that. Not only moon, but also the lunar mission also. This moon, sun also. Our latest launch, sun. And she also covered, very comprehensively Aditya, comprehensively all other moon missions and Aditya to a good extent. And she also touched upon NASA's Artemis and all that. So our students are awaiting eagerly, I'm sure. I don't want to be take shares, and I request students to shoot their pointed questions to our respected speaker today. And we are very, very, blessed to have here. At this point, in particular, this time is a very, very unique time for the entire nation, and the students are eagerly looking forward for this kind of an opportunity to listen directly from the mouth of science. So thank you very much, and we I don't know how to thank you and your team for doing all these things, and also helping a Space Club and associated activities to get a glimpse of what has happened on 23rd August and subsequently. Thank you very much. And Varun is there, isn't it? Please guide the students to raise questions. Thank you.
Okay.
Thank you very much.
Sir, I request Navani to coordinate the question answer session.
Hello, sir.
That, thank you. Adil Prajesh, just a minute. You can ask your questions. Thank you, ma'am. Thank you for your session. We are so excited by the talk you have given to us. So I request Navani to handle the question answer session. As Adil already switched on his mic, with the permission from Navani, I request Adil to ask your questions.
Hello, I am Adil Prajesh.
Adil, hello. Excuse me. Hello.
Yeah, Adil.
Yes.
Yeah, can you just hold for a minute? Like, I just have to say something to all the students here. So, hey, my name is Nimit, and I'm actually a student. So, before we start the session, and Adil, before you ask the question, I have a couple of instructions. Like, we have arranged the session so that the students can directly ask their questions to the speaker. So, can you request all the students who have a question to raise their hand? After we will speak ask the question. Hello?
What happened?
Hello?
What? Navneet, what happened?
Yeah, what, like, am I audible right now?
We had called Adil, let Adil something, then you come.
Yeah, okay, sir. Adil, please ask the question.
we taking the matter of Venus, Mars, Moon, Europa, moon of Jupiter, Titan, moon of Saturn, which is most similar to Earth.
When we talk about Venus, Venus is always called as a twin sister of Earth, and it is always called as basically the evil sister. So when we talk about the size of the planet, for example, Earth and Venus are quite identical, and they are formed during the same time. But when we talk about their atmospheres, they are really very different. For example, Venus has a very thick carbon dioxide atmosphere, whereas Earth has a nitrogen-dominated atmosphere, and the pressure is also very high. Surface pressure of Venus is very high compared to that of Earth. So, similarly, when we talk about Titan, Titan has a nitrogen-dominant atmosphere. Titan is the only other body which has a nitrogen compound dominated atmosphere compared to Earth, but there are significant differences because it spends some time in the Earth Saturn's magnetosphere and so on and so forth. So and when we talk about the Venus also doesn't have an intrinsic magnetic field, whereas Earth has. So when we talk about when we compare these planets, there are similarities. For example, if you take Venus and Earth, there are similarity in terms of size. Whereas if you take the most dominant compound in the atmosphere, Earth and Titan are similar. But it doesn't mean they are similar in all respects, because each of these has very unique characteristics also. So that is a very interesting area of research now, which is called comparative planetology.
Okay, my next question is,
Yes.
we can make lightning on space.
Mone, let Navani start the question answer session, Mone. Adil,
Okay.
please wait, Mone.
Okay, sir.
Navani, please go ahead.
Am I audible right now?
Yeah.
Yes, you are.
Yeah, I just ran into some technical glitch earlier, so I'm sorry for that. So getting into the question answer session, we already had our first question from Adil. So thank you, Adil, for your question. Now I hope that the whole instructions are clear. You can ask a question. Before that, you have to raise your hand, and I'll call you out one by one. So we have the first hand from Adidev. You may please ask your question.
Am I audible?
Yes, you are, Adil. Adi.
Ma'am, my main question now is, recently India signed the Artemis Accords. So what will ISRO do involving the Artemis program now?
Sorry.
Ma'am, recently India signed the Artemis Accords. So what will we do involving it in ISRO?
Oh, that's a real policy makers may be able to decide. I don't have any idea about any plans right now.
Thank you, ma'am. May I ask another question, please?
Yes.
Ma'am, at the start of the slideshow, you showed two images of the Earth's, of the moon's near and far sides. So why does the near side have more craters and mares compared to the far side?
This is called. This is actually the region. The moon has formed by an impact of a Mars-sized object to Earth, and during this formation itself, there is a dichotomy which is happened, and also when it evolved like the basaltic plains are on the one region, and that is the mare regions, which are seen in the near side or the visible side, whereas the other region is not having that much basaltic in nature, so that mare regions are looking more as a plain region. This has reasons even lie in the formation due to the impact itself.
Thank you, ma'am.
Thank you, Adidev, for your question. Next, I invite Surijit to pose his question. Surijit.
Hello.
Hello. Hi.
Am I audible?
Yes.
Okay. Good evening, ma'am. I wanted to ask that now India has 3 satellites on Mars, Moon, and the upcoming satellite Aditya L1 for the Sun. Is there any other upcoming projects for other planets as well?
See, we have been talking about Venus mission for a while, but formal even the Prime Minister was talking about Chandrayaan, or we will be going to moon, the Venus in the future like that. But there are no formal approvals yet.
Thank you, ma'am.
Thank you, Surijit. Well, before moving on to the question, I would like to say to the students that this is once in a lifetime opportunity. It might be because today with us we have an eminent personality who has the hands-on experience on the wonderful Chandrayaan 3. So I urge students to actually utilize this opportunity and post the questions they have regarding the world of space. So moving on to our next question, we have Adil again. Adil, you may ask your question.
I think if we produce a lightning on Earth like space,
Yeah.
if we make a lightning on space, that will we go rustly, unrustly or not?
If we produce a lightning on Earth,
Not Earth, on space.
space,
What will it do?
okay. Lightning, as we see in the case of Earth, requires an atmosphere. So, for example, in the case of Venus, people are thinking about detecting lightning. So, yeah, there can be other planets which has lightning.
Okay. Thank you, Miss.
Thank you, Adil. Well, we can move on to the next question. It's by Abhinand Krishna K. Abhinand, please ask your question.
Sir, am I audible, miss?
Yes,
Am I audible?
yes, yes.
So, if ISRO is conducting a new Chandrayaan 4 mission, then what will be the current missions? Main missions?
Sorry, meaning I have no idea about any plans for the Chandrayaan 4 mission. Right now, once we had Chandrayaan 2 time, we had the objective for soft landing, which we couldn't achieve during Chandrayaan 2, and which was later on achieved like now in the Chandrayaan 3. As of now, I do not have any information about a future Chandrayaan mission.
Abhinand Krishna. Hello, Mr. Abhinand Krishna. See, and other students. See, here you can ask Dr. Smitha about what is all about Chandrayaan 1, 2, 3 and Aditya. But what is going to be future, etc. What happens, a scientist working in ISRO will not give you a formal answer unless there is a government approval for any project. See, if there is a 4th Chandrayaan 4, it may be being worked out in ISRO, but they will not be able to tell you, because once you tell, it will be formal. Formal means government approval is required. So ask questions about what's happening in today, what is going to be a future project, Unfortunately, you should not use this occasion. We can do it later.
Okay, sir. I also have another question, which is based on what's the fuels difference in Chandrayaan 1, 2, and 3?
Chandrayaan 1 was an orbiter mission with a moon impact probe. As I told, it was not a controlled landing, was not planned. That was an object or a small craft which was crashed on near the south pole of the moon. Basically, Chandrayaan 2 also had an orbiter which is similar to Chandrayaan 1, but in a polar orbit. and also it had the lander craft and rover within. The orbiter mission is working even now successfully and providing its data, whereas at that time lander and rover lander couldn't operate. So in the Chandrayaan 3 mission, and the lander and rover were only there, and there was no separate orbiter module. Instead of that, there was a propulsion module which took the lander and the rover. Rover is within the lander, and it took up to a region which is very near to the moon. And this propulsion module itself had a payload called a shape, which is for the observations of the spectral polarimetric signatures of the Earth. So it didn't have a separate orbiter, and the rover was to communicate with the lander, and the lander was to lander in the Chandrayaan 3 can have capability to directly communicate with the Earth, and Chandrayaan 2 also to the Chandrayaan 2 orbiter. So that's the difference.
Thank you, Miss.
Thank you, Abhinand. So next, moving on to the next question, we have Mr. Raji Menon. You may please ask your question, sir.
Miss, can you hear me?
Yeah.
Miss, which gave a bigger benefit for space research for India, Chandrayaan 1 or Chandrayaan 3?
Chandrayaan 3 is a very high technologically very advanced step because it could land on the lunar surface. Chandrayaan 1 is an orbiter, and we have orbiters in other planets, like for example interplanetary orbiters we have also proven in terms of Mars orbiter mission. But if you talk about science, the Chandrayaan 3 science is yet to come formally. Papers are yet to come. People are still analyzing the data. Whereas Chandrayaan 1 is now had lot of scientific discoveries, including that of water. That's why we talk about pre-Chandrayaan 1 and post-Chandrayaan 1, because of the discovery of the presence of water. But we also expect that such path-breaking results will come from Chandrayaan 3 as well.
Miss, may I ask another doubt?
Yeah.
Why from 1976 to 1990 there were not a lot of spacecrafts to moon?
This is a very interesting thing. It is in the case of 1950s, what was happening was actually a space race between the United States and the Soviet Union. That was the time people call as a Cold War era. So once that, and it actually a very final or a very big step was the moon, human landing on moon, where United States could claim success over this space race probably. But afterwards, the space race of Cold War ended, and that's how it also they stopped their Apollo programs and all. And afterwards, the renewed interest came because of the scientific importance of the moon. Probably earlier time it was driven by more of a competitive spirit. That's why you see in the 1950s and 60s so many landing missions or moon missions. Probably Kuti sir, would you like to comment on this?
You have put it up appropriately. You have. See, there can be many reasons for it. One is that, as Dr. Smitha said, the Cold War, the one wanted to win over the other. So that has happened in some way. Russia got the upper hand. US got the upper hand. Then, nothing. But one thing we must all know, a space mission is a very costly affair. If you have to go for a space mission, you have to invest a great deal of things. So that kind of, and that investment should result in a very significant thing. So science had achieved something by that time. So it had to make further steps only after the nations come forward. So other nations, like India, etc., we hardly had any money for even our very immediate things like IRS, Indian remote and satellite, INSAT. These were our immediate requirement, our bread and butter. So once you get bread and butter only, you should go for payasam. So it is like that. It is something bigger things you go when you have resources. So that is also. So there will be multiple reasons. This is only I am only touching the tip of the iceberg only.
And also, when we had our space program, as you all know, Vikram Sarabhai's vision was that it should benefit the mankind. So when we started our space program, our primary interest was to how it can benefit by, say, communication satellites and things like that, like EduSat, or how each area of space, each area of human life could be benefited by space. And later on only, we started venturing into scientific exploration, because scientific exploration is also a fundamental or very important aspect that we could start doing that at a later phase, isn't it, sir?
Yeah, it is very correct. See, in 2003, after we achieved what Dr. Smitha said, that we have almost acquired whatever we wanted, our farmers, fishermen, a common man wanted. Then only a thinking came in 2003 of going to moon. So a committee was formed and things like that. So these are all things, which will happen in under certain circumstances. The favorable circumstances have to come.
Thank you, sir. And thank you, ma'am.
Thank you, Akud sir, for your participation and the information that you provided. Now, moving on to the next question, we have X49 Quest. So I request X49 Quest to introduce themselves and raise the question.
Ma'am, my name is Ryan, and my question is, if solar winds, okay, solar storms or solar winds, can Aditya L1 detect it, or is Aditya L1 affected by these phenomena?
Yeah, solar wind, basically solar transient events or solar wind. Solar wind is always present with particle densities of few centimeters per second, and typical solar wind velocity of around 400 to 400 kilometers per second. When this transient event happens, solar wind density can change, solar wind velocities can increase. And we have two payloads, PAPA, that is Plasma Analyzer for Package for Aditya, which is developed by SPL itself and VSSC. And there is another payload which is called Aspects. These are on board. These can give the particle measurements. So and also when these solar storms occur, the magnetic field, because this particle is the solar wind particles are in a plasma state, which is called frozen in with the magnetic field. This is a highly energetic particles, and magnetic field is associated with them. So another important variable which is to measure is the magnetic field. So that also we have a payload. So it can detect the solar storms. Yes.
And ma'am, can solar storms cause damage to Aditya L1?
No, because when we design an instrument, in such a way expecting the conditions in the environment. So Aditya L1 is designed to measure the solar wind. So it has to qualify so that it doesn't damage the instrument because of a solar wind. Yes.
Thank you, Miss.
And all the space, all these kind of satellites like Aditya L1, NASA also has similar satellites like ACE, Wing to discover. These are all designed and they are living more than 10 years in space.
Okay, Miss. Thank you.
Yeah.
Thank you, Ryan. Thank you, ma'am. Moving on to the next question, I invite Lal to put this question.
Hello, good evening all. I'm very new to this group, and so luckily I actually just made a call to Lisa today afternoon, and so he just informed me about this group and this type of a meeting. And so I'm actually into space electronics company, an associated company, and we are working in this field actually, electronic system design sector. And we have been associated with some of the aerospace companies in Europe, and we are doing the electronic system designs. And so very happy to know this type of a group, and I'm very excited and happy to know that a lot of students actually really eager to know this type of science stuff. And Smitha ma'am, it was a really wonderful session. You covered almost every aspect actually, and real inspiration, and it is a real inspiration for us also, because I happen to see that a lot of students actually eager to know lot more from this type of session, and so I feel I also need to do much more actually towards these type of things. Thank you, thanks a lot all the team behind this, really.
Thank you. And this is a very, I also have been associated with UL Space for the last time. So this is a very interesting or very useful platform for the student. I also appreciate the people behind Kuti sir and the people behind this for such a wonderful platform for the students.
Thank you, ma'am. Next, hello?
Yeah, please.
Yeah, sorry, I had another technical glitch. So, so far we have completed all the questions that were asked. So, I think it's time for us to stop the question and session. It's 4:45. So I thank each and every single one of you students and all the participants here for participating in this event. And thank you, ma'am, for this wonderful event in which you shared with us all your experiences and all this credible information regarding this wonderful space odyssey of our country. Thank you, ma'am. Now I officially conclude the question and answer session.
Thank you, thank you.
Yes.
It was really nice to talk to all of you. Yeah.
Thank you, ma'am, and thanks, Navneet, for coordinating the question and session, and all the best and congrats to all students who have asked the curious question to our guest. Once again, thank you, ma'am. Thank you for an exciting session. Keep supporting our student initiatives, and there's a student group growing up with a great enthusiasm towards space, science, and technology. And most of the students we met in recent days are doing hands-on projects also. So we'll be very much excited to get your support for our future initiatives.
Always there. Always there. Thank you so much.
So before going to vote of thanks, as I mentioned, there will be a quiz competition on the basis of moon exploration. There will be only few questions, and the first answer will be given a prize by UL Space Club, and the prize is sponsored by Cinderbe Nurture, who is a continuous supporter of UL Space Club. The quiz link will be posted in the chat window while the vote of thanks will be happening. So all of you, please try to attend the quiz. Now let me move on to Shajit sir for conclusion of the event. Sir.
Okay, thank you, Varun, and we all enjoyed this, and we celebrated ISRO victory with this talk. That's a thing happened here, and we expect a few more things from this same institute and the same speaker in future also. It was a interesting sessions, and next webinar also we are waiting for the next Saturday with a new speaker, and there is a new post, and request all the children. We will share all the links to everybody. And then you can come, and we have 250 capacity. And today we have more than 125 students here and teachers, and we'll continue this thing. And a heartful thanks to Smitha ma'am for speaking with our children. I am talking to one of our viewer. He told me that it was a really heart touching, and it was a really teaching like experience he got from your lecture. So we have recorded that, and it's there for the children to see it in future. Thank you, ma'am, very much for cooperating with us.
Thank you, sir. Thank you for this wonderful opportunity to talk to the students. This was very good. Thank you for
It's wonderful. It is wonderful for us because these the students have been longing, have been wanting to ask all these things and know all these things, and the right time we could get you, Dr. Smitha, and you very well cooperated and very well the very first talk itself we agreed to come, and you have performed very nicely to the satisfaction of our student. But to quench their thirst is not that easy, but that has happened very nicely. So thank you very, very much, and we will be again seeking your support and help. Thank you very much.
Definitely, sir. Anytime.
Please convey our regards to Dr. Rajiv, who has been okay. So nice. Shajil Mash, anything?
Nothing more, sir. Now we are concluding, and a great thank to ma'am once again for being with us. Okay, thank you, ma'am. Thank you very much.
Thank you very much.
Thank you.
Hello, sir.
Okay, ma'am.
Am I audible?
Yeah, you are.
Ole.
Okay.
You are.
So, good afternoon, everyone. I'm Devananda Srijit from 8th, and today I must say that I deem it a great honor to propose a vote of thanks to all who have helped in making this webinar a resounding success. And I'm grateful to the esteemed delegates of our session for this efforts and presence. I extend my sincere thanks to our Honorable Chief Guest, Dr. Smitha Thampi, for taking time from her busy schedule to interact with us and to help us understand better about the moon. Thank you, ma'am. And I also thank the UL Space Club and founder, Mr. Kuti sir, for giving us this wonderful opportunity. And thanks to this session, we got to know much more about the moon, a celestial neighbor, and many missions. Thank you, sir. Thank you, ma'am.
Thank you, Devananda.
Okay, Devananda, you have done a great job for this, expressing the gratitude for this program.
Thank you.
Okay, and we thank Bhavan's school Ramanatiyara also, and they told me that there is 3 or 4 ISRO scientists come out from that schools and as alumnus there. Okay.
Yes, sir.
Yeah.
We have currently two working in ISRO. Our former students.
Okay. Thank you, sir.
Thank you, Shajil sir. Thank you, Smitha ma'am, and Kuti sir. Thank you so much for the opportunity, and we are eagerly looking forward to have many programs like this along with our children and staff. Thank you so much.
Thank you.
So I have done one thing, as there are more students in this session other than our previous session.